This video will introduce you to database systems.
Data is the lifeblood of modern systems. It can take many forms: numbers, text, images, or even audio recordings, and serves as a mirror of real-world activities. Once collected, data is processed to support countless tasks, from predicting weather patterns and guiding financial investments to monitoring the global spread of pandemics. The nature of data is not uniform. It varies significantly in scope and scale.
Data is more than just numbers on a spreadsheet. It's the information that captures how real-world systems function. It can take many forms: numerical values, written text, images, audio recordings, or even video streams. A phone's proximity sensor, for example, produces raw numerical readings, while satellites orbiting the Earth capture vast collections of images. Together, these different formats allow us to forecast weather, analyze financial markets, or track the spread of global pandemics. The scale of data also varies dramatically, depending on the context. A small shop might only need to keep track of a few thousand items in its inventory, while a global e-commerce platform must manage billions of products at once. This contrast shows how data adapts to the size and complexity of the system it represents. Access to data is another important dimension. Some information is private, such as customer purchase histories used by retailers to identify buying patterns. Other datasets, however, are made public, often by governments, because they are considered essential for transparency and accountability. Historically, data was stored in analog form, encoded as continuous variations on physical media. Today, digital technologies have transformed how data is produced, accessed, and shared, making it a central resource for decision-making in nearly every field. In the past, information was stored in analog form. Audio, for example, was captured as vibrations pressed into vinyl records, while images were preserved through chemical reactions on celluloid film. These methods relied on continuous physical variations to encode data. Today, however, most data exists in digital form. It is represented as streams of zeros and ones stored on electronic or magnetic media. This transformation from analog to digital has revolutionized how information is managed. By making data easier to store, retrieve, and process, the digital shift paved the way for the development of massive computer databases. These databases now serve as the backbone of modern systems, enabling everything from global communication networks to advanced analytics that drive decision-making across industries. In the past, information was stored in analog form, relying on physical media to capture reality. Audio, for example, was etched as vibrations onto vinyl records, while images were preserved through chemical processes on celluloid film. These methods encoded data as continuous variations, reflecting the technology of their time. Today, however, data is overwhelmingly digital. It is represented as streams of zeros and ones, stored on electronic and magnetic devices. This transformation from analog to digital fundamentally changed how information is managed. By making data easier to store, retrieve, and process, the digital revolution enabled the creation of massive computer databases. These databases now serve as repositories of knowledge, powering websites and platforms that share public datasets with researchers, policymakers, and the general public. The shift to digital data not only expanded the scale of information storage, but also democratized access, allowing individuals and institutions worldwide to tap into vast resources that were once limited or inaccessible. To deepen your understanding of public databases, imagine working through an exercise that explores how these systems function and what they provide. Public databases are repositories of information, sometimes vast, sometimes specialized, that are made accessible for research, policy, or everyday use. Engaging with them allows you to see firsthand how data is organized, stored, and shared. By examining different examples, you begin to appreciate the diversity of these resources. Some databases focus on scientific research, offering datasets on climate change or medical studies. Others provide economic and demographic information, helping governments and businesses make informed decisions. Still others are designed for transparency, publishing public records, or open government data. Working through such an exercise is not just about memorizing names of databases. It's about recognizing their role in modern society. They serve as bridges between raw information and meaningful insights, enabling individuals, organizations, and communities to make better choices. In this way, exploring public databases becomes a practical test of how well you understand the flow of data and its impact on the world around you. A database is essentially a structured collection of information designed to keep data organized and consistent. While in theory data could be recorded on paper or even inscribed on clay tablets, in practice, modern databases are almost always stored electronically. Their structured format ensures that similar types of information are captured in a standardized way, making it easier to retrieve, analyze, and compare. In today's world, databases are immense, often holding trillions of bytes of information and supporting thousands of users at the same time. Because of this scale and complexity, they cannot be managed manually. Instead, sophisticated software tools are required to maintain them, ensuring that data remains secure, accessible, and reliable. These tools handle everything from managing multiple simultaneous queries to protecting sensitive information, making databases the backbone of modern information systems that power businesses, governments, and research institutions alike. A database system, often referred to as a database management system, or DBMS, is specialized software designed to handle the reading and writing of data within a database. Its role goes far beyond simple storage. It ensures that information remains secure, internally consistent, and accessible whenever needed. These responsibilities become especially demanding when dealing with massive databases that contain vast amounts of data and serve thousands of users simultaneously. To meet these challenges, DBMS platforms are built with complex features and sophisticated tools that can manage such scale efficiently. Within this environment, a query acts as the user's request to interact with the data. It might involve retrieving specific information, such as customer records or financial transactions, or altering data to reflect updates and corrections. Queries are the bridge between human intent and the structured world of databases, enabling users to extract meaning and make decisions from the enormous volumes of information stored inside. A query language is a specialized type of programming language created specifically for working with databases. Unlike general-purpose languages such as Python, Java, or C++, query languages are designed to read and write data with efficiency, making them essential tools for managing large and complex datasets. Because many databases are intricate, and most business users are not trained in query languages, direct interaction with the database is often impractical. This is where database applications come in. These applications act as a bridge, providing user-friendly interfaces that allow people to interact with database systems without needing to understand the technical details of query syntax. In this way, database applications make it possible for organizations to harness the power of databases while ensuring accessibility for everyday users. Programmers design applications to make interacting with databases easier, ensuring that users can access information efficiently and securely without needing to understand the technical complexities behind the scenes. Database software itself is organized into layers. At one level, applications communicate using a query language, while at another, the query language interacts directly with the database system. Beneath these, additional layers such as the operating system provide further support, though those details extend beyond the scope of this discussion. It's also worth noting that the term database can sometimes be used interchangeably to describe not just the data itself, but the entire system that manages it. This dual meaning reflects the close relationship between the structured information stored and the sophisticated tools required to keep it consistent, secure, and accessible. In this material, the word database is used in two different ways. Sometimes it refers to the actual collection of data itself, while at other times it describes the entire system that manages and organizes that data. Although the term can carry both meanings, the intended sense is usually clear from the surrounding context. Here, both interpretations are applied, depending on whether the focus is on the stored information or on the software and processes that govern it. Let us test our understanding. People interact with databases in different roles, each with distinct responsibilities. A database administrator, for example, is tasked with protecting the system from unauthorized access. They establish and enforce procedures that regulate who can use the database and ensure that it remains available and reliable at all times. On the other hand, a database designer focuses on shaping the structure of the database itself. They decide how each piece of data should be formatted and how the overall system should be organized. This role requires balancing multiple priorities, such as storage efficiency, quick response times, and adherence to rules that govern the data. Because these priorities often conflict, designing a database is a technically demanding process that calls for careful judgment and expertise. Together, administrators and designers illustrate how databases are not just collections of information, but complex systems that require specialized skills to secure, structure, and optimize. A database programmer plays a crucial role in bridging the gap between raw data and practical applications. They develop computer programs that rely on databases, combining the precision of query languages with the flexibility of general-purpose programming languages. Because these two types of languages differ significantly, database programming requires specialized expertise to ensure that applications run smoothly and interact with data efficiently. On the other side of the interaction is the database user. Users are the consumers of the information stored within a database. They may request specific data, update existing records, or generate reports that transform stored information into meaningful insights. In this way, programmers build the tools, while users apply them to access and utilize the data for decision-making, analysis, or everyday tasks. Together, these roles highlight the collaborative ecosystem that makes databases such powerful engines of modern information systems. Database users typically interact with the system through applications, which provide a more accessible interface. However, in some cases, they may also submit queries directly to the database system to retrieve or modify information.